Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 5, Lesson 7 on exponential regression. Now this is really a follow-up to a lesson that we did earlier in the year on linear regression, right? We're going to be taking a data set and we're going to be fitting it now with both linear equations and exponential equations. And I really should say our calculator is going to be fitting it. It's going to be finding the best exponential equation to fit the data and the best linear equation as well. So make sure that you have your graphing calculator handy because we're going to be using it quite a bit in today's lesson. Let's jump right into it. All right, non-linear regression. In Unit 3, we saw how linear functions can fit a bivariate data set. In other words, two variables, x and y. In the real world, it can happen that two variables are related, but not linearly. In this lesson, we will explore how to fit certain data sets with the best fit exponential curve known as exponential regression. So let's take a look at exercise number 1. A scatter plot is shown below with the best fit line drawn through the data. The linear correlation coefficient is given on the graph. Letter A, based on the correlation coefficient, how strong is the linear association between the two variables? Explain. All right, well, pause the video now and tell me, how strong is the linear association? Well, the answer is it's very strong, right? And it's very strong because that R value is extremely close to 1. All right, so it's very strong because R is very close to 1. Remember, the closer that R is to either 1 or -1, then the stronger the association is, whether it's linear or exponential or anything else, and the closer it is to 0, the weaker the association is. So an R of 0.958 is very close to 1, so that's a very strong. Now let's take a look at letter B. Look at the pattern of how the data points are dispersed, that means spread out, about the line of best fit. Do you see any patterns? All right, so I want you to take a look at this line of best fit, right? And I want you to take a look at how the data is sort of like spread out around that line and, tell me if you see any patterns. Pause the video now and at least think about these and write something down if you can. Well, we might say towards the beginning of the data set and the end of the data set, the data is all above the line. But in the middle of the data set, notice that the data is all below the line. Now, that's a little bit weird because most of the time, right? Most of the time, and we'll write that down in a little bit, but most of the time when we have a sort of linear regression, let's say, we don't see that. Let me draw the line of best fit in red. Right, what we would see is, we would see something like that, where the data is sort of spread out above and below the line all throughout the data's domain, right, all through the data's domain. But in this particular case, we see something very specific, which is, let's try that again, come on. At the beginning and end of the data set, the data is above the line. Oh man, spaces, Kirk, above the line. And likewise, in the middle of the data set, all the data is below the line. And that's kind of weird. You know what I mean? We don't really expect that if there's truly a linear association within the data. So letter C, by hand, draw what you believe is the best fit exponential function for this data set. Now remember, exponential functions, right? True exponential functions either look like this, right? They're increasing, or they look like this, right? They're decreasing. This one is clearly an increasing set of data. So we want to draw a graph that kind of looks like this and see what you can do. Draw the best fit exponential that you can through this data set. And I know that's a little bit different than drawing a line where you're like, let me see if I can get the same number of points above it and below it, general slope, all that. Go ahead and do that. All right, well for me, I of course have the magic wall, and I actually got the best fit exponential there. And notice with this best fit exponential, not only is it going through the data quite nicely, but now we see the data kind of being above and below the exponential curve all along the domain of the data set. We don't have this weird, oh, it's all below here, it's all above here, it's all above here, right? That data is kind of dispersed evenly above and below the curve of best fit throughout the domain of the data, all right? And that's what really kind of tells us that in this situation, right, an exponential curve, even though the linear curve shows a great association, wonderful 0.958, right? Even with that, we sort of suspect the exponential should be better. Okay. When data has, in general, a curved pattern that only increases or only decreases, then it makes sense to try to fit the data with an exponential function. These types of functions come up often in population growth. So let's take a look at an example of that in exercise number 2. The population of Jamestown has been recorded for selected years since 2010. The table below gives these populations. So in 2012, the population is 5,564, etc. Letter A. Use your calculator to determine the best fit exponential equation in the form y equals a times b to the x, where x represents the number of years since 2010, and y represents the population. Round a to the nearest integer and b to the nearest thousandth. Give an interpretation of the values of a and b in the context of the problem. Whew, there's a lot there. All right, so let's go through it. We've never done an exponential regression on our graphing calculators. I'm going to be using the TI Inspire. So let's start off. Let me grab my worksheet so I've got it. All right, let me actually just, I'm going to do a brand new document. Let me escape. Doc, file, new. Nope. So I'm going to add a list in a spreadsheet. First thing I always do when I do regression is I name my variables. So I'm going to, I think I'm going to call it time. I could have called it year. Doesn't really matter. And up here, I'm going to put in, I think I'll just put in pop for population. Okay, now remember, X is the number of years since 2010, right? So 2012, I just want to put a 2 in there. 2014, I want to put a 4. 2015, a 5. 2017, a 7. 2019, a 9, right? Now, I want to put my populations in. Those are easy. 5,564. Want to be careful entering the data. 6,121. 6,300. Any number that gets entered incorrectly will throw off my regression equation. So I always want to do them very carefully, right? I want to make sure I've got them all right, even when I'm doing these videos, right? 5,564, 6,121, 6,300, 6,812, 7,422, 2, 4, 5, 7, 9. It's all good. All right. So I've got all my data entered correctly. Again, if I make a mistake there, my exponential regression equation will be incorrect. And there's no way somebody who's like, let's say, grading a standardized test of yours can have any clue what you did wrong, right? Because they can't see your data set. All right, so now what I'm going to do, I'm going to hit menu, all right? I like choice 4, statistics, all right? I want to go to statistical calculations, so I'm just going to hit enter. Now I see all sorts of things here, including my linear regression. I have to look all the way down here to letter A, exponential regression. And again, this is going to be different depending on whether you're using a TI-83 Plus, an 84 Plus, a TI Inspire, a Casio, a Hewlett-Packard. It's going to be done always just a little bit differently. I want my exponential regression. In my X list, I need to give it my X values, and that's going to be time. All right, my Y value, no. My Y list is going to be population, And everything else I'm good with, I'm going to hit OK. All right, generally, once you get your x list and your y list in there, you don't really have to be concerned with anything else. Here they show you the general form of your exponential regression equation, a times b to the x. They immediately give you the value of a, that's 5,158 rounded to the nearest integer. And let's see, we wanted the value of b to the nearest thousandth. So to the nearest thousandth, that'll be 1.041. 1.041. So let's get that thing in there. Let's go back to our full screen. Our equation is going to be y equals 5,158 times 1.041 to the x. Great. Now, let me make that decimal point a little bit better. It also says to give an interpretation of the values of a and b in the context of the problem. Well, remember, a is always your y-intercept. The value when x is equal to 0. X is the number of years since 2010, so we can say the population in 2010 was 5,158. And now let's talk about b, right? This is the value of b, 1.041. That tells us that the population is growing at a rate of 4.1% per year. And is growing at a rate of 4.1% per year. All right, fantastic. There it is, right? You know, we plug the data in, we tell it to produce an exponential equation, and we have it. This is absolutely no different than our linear regression. The only difference really at all is which type of regression we pick. Let's take a look at letter B. Algebraically determine the number of years to the nearest year for the population to reach 20,000. Fantastic. So what we want to do is we want to solve this particular equation. And we want to do it algebraically. All right. Now, in our last few lessons, we saw how we could use logarithms to solve exponential equations. Pause the video now and see if you can solve this equation using a logarithm with an appropriate base. All right, let's do it. So the first thing I'm going to do is divide both sides by 5,158. Great, that gets rid of that. So now I have 1.041 to the x is equal to 20,000 divided by 5,158. Remember, I'm not going to even think about what that ratio is. I'm now going to take the logarithm base 1.041 of both sides. I wonder if I can just scoot this. Nope, I can't. That would have been great. And of course, oh my goodness, it's all breaking down now. So I'm going to take the log base 1.041, man, of this side as well. That's going to cancel that exponential. Oh man, that was 1.041. There we go. Sorry about that. That cancels that, which gives me x, which is what I want, being the log base 1.041. Very different 1.014 versus 1.041. And then I just do that on my calculator using the generic log button. And I will end up having 33.726, etc., which to the nearest year is 34 years. All right, sorry about that base snafu there. My mind kept wanting to take the 4 and the 1 and flip-flopping them. All right, but that's it. And this, of course, has nothing to do with exponential regression. It has to do with how we solve exponential equations using logarithms with an appropriate base. And the base in this case, 1.041. All right, let's keep going and doing a little bit more work with exponential models. Let's take a look at a decreasing model. Just like with linear regression, exponential regression can include both increasing and decreasing examples. Let's take a look in exercise number 3 at one where we have a decreasing data set. Ji-Hoon is running an experiment to see if time spent on social media has any relationship to performance on a math quiz. He randomly selects 10 people and asks them to record their average time on social media and then gives them a 50-question math test. Yay. The results are shown below. All right. So, Ji-Hoon's premise here probably is the more time you spend on social media, the worse you're going to do on this math test, probably because you spend less time studying. I don't know. You know what I mean? So, somebody that spends 49 minutes per day on social media ended up getting an 11, 74, got a 13, etc. Now, let's take a look at letter A. Use your calculator to produce the best fit exponential equation in the form y equals a times b to the x, round a to the nearest integer, and b to the nearest hundredth. All right, well, why don't you go ahead and do that, and then we'll put the data in our calculator and look at that regression itself. Take some time to do that. All right, well, again, I've got to be a little bit careful here. Let me open up the calculator. I'm going to go to a brand new document just so that it's easy. I'm going to go into my spreadsheet. Here, I want that to be time, I think. And then we'll go here and we'll maybe put in score. C-O-R-E, great. Nope. Apparently enter doesn't work there. Here we go, just real quick. 49, 74, 31, 14, 93, 84, 37, 5. That person doesn't spend much time on social media. 42 and 60. Make some social commentary while I go. Let's see, an 11, 13, 27, 28. Those people are probably cheating off each other. 9, 4, 19, just kidding. 39, 21, and 16. Okay. Feeling pretty good about that. I think I got all the data correct. We'll find out really quick if my exponential equation matches what I've got on the sheet, assuming what I've got on the sheet is correct. So I'm going to hit menu. I'm going to go to statistics, statistical calculations. I want exponential regression. In my X list, again, I'm looking for my time. In my Y list, I'm looking for my score. Everything else is fine. I'll just hit enter. And wow, I gotta go way up here, but there it is, right? So in this case, right, I can see immediately that my A, which I want to the nearest integer, is gonna be 42. It's 41.8, etc. It's messy because it's a regression. My B, which I want to the nearest hundredth, is going to be 0.98. Good, it matches what's on the sheet. Probably means I put the data incorrectly, or just ironically, I put it in incorrectly exactly the same way. So that means now that my regression equation is simply y equals, now maybe we'll go back into here real quick, y equals 42 times 0.98 to the x. And we could do all that kind of interpretation business again. 42 is the score you'd expect somebody to get if they spent no time on social media, and you're getting a 2% decrease per minute that you spend on social media in terms of how many questions you got correctly, etc. Now let's take a look at letter B. What is the correlation coefficient for this exponential fit? Round to the nearest hundredth. Give an interpretation of what this coefficient tells you in the context of the problem. Well, the correlation coefficient is still the R value, regardless. So what I'd like you to do is pause the video right now, take a look at your calculator screen, pull off your R value, round it to the nearest hundredth, and then try to do an interpretation. Pause the video now and go ahead and do that. All right, well, let's find that R value real quick, right? So if I come back in here, I can see actually, I'm actually highlighting it right now. My R value is negative 0.877, etc. To the rounded to the nearest hundredth, that's negative 0.88, right? Yep, to the nearest hundredth. So R equals negative 0.88. And what that tells me, right, kind of two things. One, the fact that R is negative, and two, the fact that R is fairly close to, but not really close to -1, right? So the first thing I know is that there's a negative association between time spent and the score on the math test, and it's a moderately strong or fairly strong. It's not really strong, but it's fairly, right? So I'm gonna say there is a fairly strong negative association between time on social media and let's call it math score. All right, so there's a fairly strong negative association between time on social media and math score, meaning that in general, as the time on social media goes up, right, the time or the score on the math test goes down, and as predicted by an exponential curve, all right? But now, let's take a look at C. Using the same data set, find the linear regression equation in the form y equals ax plus b, round a to the nearest hundredth and b to the nearest integer. Also state its correlation coefficient to the nearest hundredth. Now you might say to yourself, oh, this is going to be a pain. He's going to have to enter all the data again, open up a new spreadsheet, all of that. You don't actually have to do that. In fact, all you need to do, we just come over here. We're going to go back to menu. We're going to go back to statistics, back to stat calculation. I'm going to go to linear regression. My X list is going to be a little bit ugly. Nope. This emulator. My X list is going to be a little bit tricky because there's all sorts of weird stuff in here now, but there's time again. I still want time to be my X list. And now my Y list, I still want it to be score. Okay? And now it will just naturally put everything in the right place. So what's now happened is that all of my linear regression work has just been kind of shoved over two columns, so it didn't replace my exponential regression. It's just sitting two columns over. So now what I've got, right, is I've got my y equals mx plus b. My m is negative 0.3297. I'm going to want it to the nearest hundredth, so negative 0.33. My y-intercept, which I want to the nearest whole number, is going to be 35. It's 34.89, etc. So I'm going to round that up to 35. And my r value is negative 0.9164, so we'll round that to the nearest hundredth. All right, get all those down. Let's go back into our full view. So we've got y equals negative 0.33x plus 35, and an r value of negative 0.92. Okay, letter D. Which model, exponential or linear, predicts the higher value of math questions answered correctly for a person who spends no time on social media? Justify. So if somebody didn't spend any time on social media at all, which of the two models would predict the higher score on the math test? Pause the video now and answer this question. All right, well, we've got our nice linear model sitting right here. Our exponential model's a little hidden, so let me write the exponential model right here. That's going to be 42 times times 0.98 to the x. Okay, so, well, what do we think? Well, the linear model, it's going to predict when x is 0 that 35 questions are going to be answered correctly. And the exponential model is going to predict 42 questions answered correctly. So it's going to be the exponential, right? For x equals 0, exponential model predicts 42, and linear predicts 35. So exponential predicts higher. All right. Now, I mean, that doesn't mean it's a better model or a worse model. Just simply says, that the exponential is going to predict 7 more questions correct out of 50 than the linear model does. All right, last question. Exercise 4. Even though the linear model had an R value closer to -1 in exercise number 3, why might the exponential model still be the better choice based on the long-run behavior of the two types of functions? Explain. Illustrate graphically. All right, so again, this is interesting, right? The exponential, let's just kind of get these down. The exponential had an R value of -0.88. All right, pretty close to -1. The linear model had an R value of -0.92. So based on the R values alone, you might expect the linear model to do a better job predicting, right, the performance on the math quiz based on time spent on social media than the exponential model would. But if we actually kind of looked at their scatter graph, right? So here's the data set. Here's the exponential curve of best fit. Here's the linear curve of best fit. Why might the exponential model make more sense, especially in terms of the long-run behavior of the two types of functions? So again, as sort of like the time spent on social media gets larger and larger, this graph stops at 100 minutes, but of course, we could have a person spending 300 minutes in a given day on social media, or even longer than that, right? Why might the exponential model be better? Pause the video now and see if you can figure that out. Well, the real key is, and let me kind of change to red here. The real key is that eventually that linear model is going to go below the x-axis. So there's going to be a point at which the linear model is going to predict a negative score on the math test. On the other hand, the exponential model is going to just get closer and closer to the x-axis, but never hit it, because the exponential model is going to have a horizontal asymptote of the x-axis, right? So the score is going to get lower and lower as time spent on social media goes up and up and up, but it's never going to get below 0 because of the horizontal asymptote. And that is a lot more realistic than, let's say, it going negative. So the exponential model will never go below the x-axis because, and that red pen is coming out whenever it wants to, because it has a horizontal asymptote of the x-axis. The linear model, beautiful. The linear model will eventually become negative, which is unrealistic. We can't have a negative score on our math quiz, right? That's just not possible. But it's very clear, right? Somewhere around 100 minutes spent on social media, the linear model after that is going to predict a negative score on the quiz. The exponential model, no matter how far out you go, will never predict anything negative because it's going to flatten out the closer and closer it comes to the x-axis. All right. One of the things that's really cool about linear and exponential functions is that they're some of the few functions that are truly always either increasing or always either decreasing. So sometimes in the real world, we have bivariate data that comes in pairs, an x-coordinate and a y-coordinate, that should either always be increasing or always be decreasing, or at least it looks like it is when we put it on the scatter graph. Sometimes that data more or less falls along a straight line, right? Sometimes it curves. When it does curve, oftentimes an exponential model is a better choice in terms of trying to use the data to predict other values, all right? But whether it's better or not can be both determined based on our values or really based on the physical scenario that's going on, right? Like we saw in that last problem, the linear model had a better R value, an R value closer to -1. And yet, realistically speaking, the exponential model made a lot more sense. For you definitely want to be able to think about those issues, but also you just want to be able to get the data into your calculator and produce the appropriate model. All right, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.